In this video, we will be going over the AP Fluids FRQ questions and their answer documents. Starting with the 2017 exam, two students observed water flowing from left to right through a section of pipe shown above, which decreases in diameter and increases in elevation. The pipe ends on the right where the water exits vertically. At point A, the water is known to have a speed of 0.5 meters per second and a pressure of 2 times 10 to the 5th pascals. The density of water is 1,000 kilograms per cubic meter. Part A, the students disagree about the water pressure and speed at point B. They make the following claim. Student Y claims that the pressure at point B is greater than at point A because the water is moving faster at point B. Student Z claims that the speed of water is less at point B than at point A because the conservation of energy, some of the water's kinetic energy, has been converted to potential energy of the Earth-water system. Part I, indicate any aspect of student Y's claim that are correct. Part 2, indicate any aspects of student Y's claim that are incorrect. Support your answer using appropriate physics principles. Part 3, indicate any aspects of student Z's claim that are correct. Part 4, indicate any aspects of student Z's claim that are incorrect. Support your answer using appropriate physics principles. Part B, calculate the following at point B: the speed of the water and the pressure in the pipe. And Part C, the valve to the left of point A now closes off that end of pipe. The section of pipe shown is still full of water, but the water is no longer flowing. Calculate the absolute pressure at point A, the pressure that includes the effect of the atmosphere. And Part 2, an air bubble forms at point A. On the figure below, where the dot represents the air bubble, draw a free body diagram showing and labeling the forces, not components, exerted on the bubble. Draw the relative lengths of all vectors to reflect the relative magnitudes of the forces. So we're going to look in our 2017 answer document, and this was question 1. Part A1 is 1 point for indicating that student Y is correct in stating that the water moves faster at point B and not indicating any other aspect. So if we look back here, student Y claimed that the pressure at point B is greater than at point A because the water is moving faster at point B. The only part that is true is that the water is moving faster at point B. We know that the water is moving faster at point B because of the continuity equation. This has a larger area than that, so it will have a smaller speed than up there because of the law of conservation of mass. Moving on. Part 2, student Y's statement that the pressure at point B is greater than point A is not correct. So we have to correctly indicate how height affects pressure using Bernoulli's equation, so using conservation of energy principles, and correctly indicating how the speed affects pressure using Bernoulli's equation. So example, the pressure at point B is not greater because the water at point B is moving faster and is higher than at point A. The kinetic energy and gravitational potential energy terms in Bernoulli's equation are both greater. Because the sum of pressure and these two terms is constant, the pressure must be less. So if we remember, student Y claimed that the pressure at point B is greater, but because it is moving faster and it is higher up, those two terms in Bernoulli's equation will actually be larger than they were down here, so the pressure will actually decrease as you go up. Part 3, indicating any aspects of student Z's claim that are correct. There's 1 point here for indicating one of the following. Student Z is correct that stating the potential energy of the water-Earth system has increased. So the water did go up, the potential energy increased. The student Z also said that conservation of energy applies, which is true. And stating that nothing is correct or giving no response with a justification in 4. So if you did not catch this, then you could still earn this point by getting this point. So the issue with student Z said that the speed would be less as it rises. We know that's not true because of the continuity equation. If the third bullet for part 3, so if you didn't put anything in here, indicating that work is done on the water due to the pressure difference, so energy is not constant. Okay, now for the calculations. To calculate the speed, we're going to use the continuity equation. So there's 1 point for stating the continuity equation in some way, shape, or form, and then the second point is for getting the correct answer. Part 2 is for applying Bernoulli's law, or Bernoulli's equation, correctly and getting the pressure at point B. Be very careful. Make sure that you're using these y's for YA and YB. Those are heights. So for YA, it would be 0. For YB, it would be this 0.5 or this 5 meter height. Part C, we need to, where are we at? Part C is when we close off the valve here. We now have to calculate the absolute pressure at point A. So it's no longer a fluid dynamics question, it's now a static fluids question. So we're going to use gauge pressure here. And then we need to indicate that the buoyant force is upward and gravity is downward. This one, I could understand why you might not get the full credit here, because there is gravity acting on that air bubble. And that, I think, is a force that a lot of people would have missed. Okay, moving on to 2018. So 2018 and 2019's FRQs were both interesting in that they were combinations. And as such, we need to revisit the fact that in the 2020 AP exam, due to the coronavirus outbreak, we are limiting the AP exam into only including FRQ questions that cover the concepts of fluids, thermo, electricity, and magnetism. It will not be covering anything to do with light, optics, and it will not be covering any of the modern physics. So there are some parts of both the 2018 fluids question and the 2019 fluids question that had to do with those other two units that are not included anymore. And also note that is just for the 2020 administration. So let's go to the question. A large boat, like the one shown above, has a mass mb and can displace maximum volume vb. The boat is floating in a river with water of density P water, and is being loaded with steel beams, each of density P steel and volume V steel. The boat owners want to be able to carry as many beams as possible. Part A, derive an expression for the maximum number N of steel beams that can be loaded onto the boat without exceeding the maximum displaced volume, in terms of the given quantities and physical constants as appropriate. Part B, the captain realizes that oil is leaking from the boat, creating a thin film of oil on the water's surface. In one area of the oil film, the surface looks mostly green. Explain in detail how constructive interference contributes to the green appearance. Assume the index of refraction of the oil is greater than that of the index of refraction of the water. And then part C. Later, the boat is floating down the river with the water current heading for a town. The river has a width of 60 meters and a constant depth and flows at a speed of 5 kilometers per hour. Partway to the town, the river narrows to a width of 30 meters while its depth remains the same. Calculate the speed of the water in the narrow section. Part B here is an optics question. I'm not going to be addressing that part simply because it's not relevant to the 2020 AP exam. So here we have derive an equation for the maximum number N of steel beams that can be loaded onto the boat without exceeding the maximum displaced volume in terms of the values given. So we need to correctly equate the correct forces acting on the boat steel system. So we're trying to equate the force of gravity on the boat steel versus the buoyant force acting on it. We want those forces to be equal. For correctly calculating the weight of the boat steel system using this equation here. The mass of the boat plus the number of steel beams times the density of one steel beam times the volume of one steel beam. If I take the volume times the density, I get the mass of one steel beam, multiply that by the number N, and then multiply that by that whole summation by acceleration due to gravity. You must clearly label the mass of the boat. Then you need to correctly calculate the buoyant force, which is going to simply be the density of water displaced times gravity times the volume of the boat. That's the maximum volume that the boat can displace. If we displace any more than that, we're going to sink. If we displace less than that, we could have added another steel beam. And then we need to algebraically manipulate the equations to get the expression for the number of beams. So we need to set this force equal to this force and solve for n. And that will give us this equation down here. There are many different versions of this equation because you can do your algebraic manipulation in multiple ways, but it has to be algebraically equivalent. Part B is an optics question. We're not going to talk about that. Part C is actually a fluid dynamics question using the continuity equation. So we have the width times the velocity times the width times the velocity. Now, technically, this should be an area, but we don't know the area. But we do know that the area would be the width of the river times the depth of the river. And since the depth is constant, it will cancel out of the equation. You do not need to convert your kilometers per hour to meters per second because this equation is a proportionality. As long as we're still using kilometers per hour, our answer is going to be in kilometers per hour. So you have to use the continuity equation, and you have to get the right answer to earn the full credit. So while this is marked as being a 10-point question, it's actually only 6 points that we could earn from fluids. The last FRQ question is from 2019. A student notices many air bubbles rising through the water in a large fish tank aquarium. In the figure below, the circle represents one such air bubble, and two incoming rays of light A and B are shown. Ray B points towards the center of the circle. On the diagram, show the paths of ray A and B as they go through the bubble and back into the water. Your diagram should clearly show what happens to the rays at each interface. Part A is another optics question. We're not going to talk about it. Part B, the bubble has volume V1 on the air inside it has a density of rho A, and the water around it has a density of rho W. The bubble starts at rest and has a speed Vf when it has risen to a height h. Assume that the change in the bubble's volume is negligible. Derive an equation for the mechanical energy dissipated by drag force as the bubble rises this distance. Express your answer in terms of given quantities and fundamental constants as appropriate. Part C. At a particular instant, one bubble is 4.5 meters below the water surface. The surface of the water is at sea level, and the density of the water is 1,000 kilograms per cubic meter. Determine the absolute pressure of the bubble at this location. The bubble has a volume V1 when it is 4.5 meters below the water surface. Assume that the temperature of the air in the bubble remains constant as it rises. In terms of V1, calculate the volume of the bubble when it is just below the surface of the water. If the air in the bubble is cooled as it rose, the volume of the bubble would be less than the volume calculated in part C2. Use physics principles to briefly explain why. So the 2019 exam, this was question number 4. So scrolling down to question number 4. Part A is optics, gonna skip it. Part B, we typically have not really talked about work dissipated by drag force. This is a non-conserved work. Change in kinetic energy is equal to the net work done on the system. This is the work kinetic energy theorem from AP Physics 1. The force doing the work is the buoyant force. The force opposing the work is the force of gravity, and also whatever force is causing that loss of energy. We need to find the work done by the buoyant force, which would be the buoyant force times the distance traveled. We need to correctly substitute into an equation with consistent relative signs. So here we have our change in kinetic energy, 1/2 rho V1, which that together is a mass term, times a V final squared, equals, here is our buoyant force, or buoyant work, I should say. this here would be the work done by the force of gravity. I personally think that stating the work done by the force of gravity should have been its own point if the buoyant force was its own point, but that's neither here nor there. And then we have our work dissipated, and just algebraically solving this for the work dissipated. Down here we have determining the absolute value or absolute pressure in the bubble at this location. So we have atmospheric pressure sitting on top, and we have the gauge pressure adding together to give us the absolute pressure. That's just one point. It's plugging stuff into an equation. Part 2 is dealing with the change in volume using the ideal gas law. We know that the pressure times volume equals nRT, and the pressure times volume at depth is going to be equal to the pressure times volume at the surface, because N, R, and T are remaining constant. So substituting in the pressures and getting your answer. The next point is for, the next point is for correctly explaining why the value for the volume would be less if the temperature decreased. It can be a qualitative or a quantitative explanation. I would personally go with the full combined gas law here and simply state that if T surface decreases, then that means the numerator term also would have to decrease. The pressure would not be any different, but the volume would have to decrease. Another example would be, as the bubble cools, the air molecules move slower. Slower molecules exert less force on the inner surface of the bubble, so that's more of your qualitative explanation. Because it's hard to tell. It did not say briefly explain, so that would lead me to think that this would be worth more than 1 point, but we have to remember what else came before. This was a total of 10 points. There was a diagram, which is usually 2 to 3 points. There was a derivation, which is usually 3 points. So we're already at 6 points in the whole question. There's not that many points that are going to be left down here. So sometimes breaking down how many points you think each part would be worth can help you gauge how much time you should spend on each part. And that's going to do it for this fluids FRQ analysis. If you've got any questions, please sure to let me know.